to go. And that's it, right? Not even close. We're just getting started, people. Why is that? Because the data here is encoded. What is encoding? Basically, encoding is a transformation that is applied to the data before it's transmitted. Why would you do something like that? Because encoding increases over-the-air resiliency. Why is this necessary, right? Remember that we're dealing with unlicensed spectrum, right? This is what the 900 megahertz band, which is what LoRa uses in the United States, looks like. Look at all that stuff that's not LoRa, right? That stuff is there to ruin your day. It's there to create all sorts of interference and make your receiver not work the way you expect. So RF is a really brutal environment. There's all sorts of interference. And basically, the encoding is a way of treating your data so that even if you have a non-ideal reception, you can still get the data out of the frame. So what do we have here? Remember that LoRa is closed source. We have some material that's available through data sheets, but we really don't know for sure definitively what's in this PHY. So again, we're going to go back to open source intelligence, figure out what we know, and then try to narrow in on how we're going to iterate through this and figure out how it works. So from the patent, we have a number of very good clues. First of all, it refers to this stage called gray indexing, which, as is defined there, should add error tolerance in the event that you read a symbol as being off by one bit. Or basically, if you read a symbol in the incorrect bin. Secondly, you have data whitening, which induces randomness into the frame. We'll talk about that momentarily. You have interleaving, which scrambles the bits within the frame. And then you have forward error correction, which adds correcting parity bits. You can think of it as being like parity bits on steroids. Rather than telling you that just an error occurred, it can actually help you correct the error without needing to retransmit. So we have 4 different things that comprise the encoding, and they're in the patent, right? So that's awesome. It's easy, right? Why is that? Because documentation lies to us. And even and even the clearest signals can lead us into dead ends. So let me show you how. So the gray indexing we read to represent gray coding, which is just a basic binary transformation that you can use to treat data. Whitening, we actually have defined in one of the application notes reference designs for the pseudo-random number generators that are used for the whitening. It's like C code that you can copy and paste. So this should be rock solid. Step 3, we have an actual algorithm for the interleaver that is defined in the patent. And I'll show you what it is momentarily. And then finally, step 4 suggests that a Hamming code is used, which is just a standard forward error correction mechanism. So the first thing we're going to focus on figuring out here is the data whitening. And that's a critical step because basically the way the whitening works is you XOR your message against a random string. And unless you know what the random string is, you're not going to be able to make any sense of what follows it. So figuring out that pseudo-random string is essential to being able to even make sense of what follows it. So again, with whitening, you take your buffer that's going out to the radio, and you XOR it against a pre-computed pseudo-random string that is known to both the transmitter and the receiver. Then when the receiver gets in the frame, it XORs the receive buffer against the same sequence that the transmitter used. And you get back the original data because if you remember, XOR is its own inverse. So that nicely undoes itself. Now, why would we bother with whitening? And that's because having random data is really good for receivers. It's similar to Manchester encoding, where basically by encoding the data such that you don't have some number of consecutive values of some number of consecutive symbols of the same value, you get this nice random data source. And what that does is creates lots of edges for your receiver to do clock recovery against. So you get better reception of longer messages, or if your clocks are bad. Manchester, of course, comes with the penalty of a reduced bit rate. It actually cuts the effective bit rate that you can use into half of the baud rate, whereas whitening does not. The caveat is that you have to know what the string is in order for it to work. So let's find the whitening sequence. We've got these algorithms in the application note. We've got some examples in Strangelove. None of them worked. So we had to figure this out empirically. How can we do that when there's interleaving and forward error correction in the pipeline here, right? We can send something that might put the whitening in a certain state that we could leverage, right? But we still have these unknown transforms that follow it. How are we going to be able to figure out what those operate? How are we going to be able to figure out the whitening when those operations are in the loop too? Well, we need to bound the problem and make some assumptions so that we can start to iterate through this black box problem. So we're going to assume that the forward error correction is what the documentation tells us it is, the Hamming N4. And we're also going to make another assumption, and we're going to set the spreading factor equal to 8 bits per symbol. And basically, if you do that, then it makes it such that we'll have exactly one Hamming 8.4 code word per 8 bits per symbol, right? Because if we set the number of total bits in our Hamming error correcting code to 8, we have 8 bits per symbol, fits very nicely and should work out well. Now, there's another very useful property of the Hamming forward error correcting code scheme that we're also going to exploit. And that's that Hamming 8.4 contains 4 data bits and 4 parity bits each. And for 14 of those 16 states, again, remember 2 possible states per bit to the power of 4 data bits per code word. In each of those, in 14 of those 16 code word possibilities, there are 4 ones and 4 zeros each. However, for the word for data nibble 0, that's 4 zeros, the code word of that is 8 zeros. So it's totally non-additive. So if we basically if we send our forward error correcting scheme a string of zeros to apply itself to, it's totally non-additive. We get back twice as many zeros. So we can leverage that to do something to try to cancel out that forward error correcting stage. So let's go ahead and transmit a string of all zeros, right? So again, if it's Hamming 8.4 as we assume, we expect that stage 4 of the forward error correcting code to cancel out, right? What about the interleaver? Let's take a look at the algorithm that's suggested in the patent. There it is. The key takeaway from this is if this is implemented in a way that's similar to this, is this should be totally non-additive. So this should just move bits around, but not add any bits, right? So if it is in fact non-additive, and all we pass through are a bunch of zeros, what happens when you shuffle around a bunch of zeros? You get the same thing out, so that falls away too, right? So we're left with 2 states, right? We have our symbol gray indexing stage and our data whitening stage. Whitening is what we're solving for, that's our variable. And gray indexing, the quote-unquote gray indexing is a bit of an ambiguous term, but it likely refers to some variant of gray coding, which we mentioned earlier. But even if it is gray coding, reverse gray coding, or nothing at all, it's just something they didn't implement, that leaves only 3 permutations here, right? So we've just reduced all the ambiguity of figuring out what this decoder is to really or figuring out what the whitening sequence is to really just figuring out which of the 3 states, which of the 3 operations this first gray indexing stage is, right? So if we do that and we try all 3, that's only 3 things to attempt in order to derive the whitening sequence from the transmitter. Because again, if we send through a string of zeros, what does the whitening do? It XORs the zeros against the pseudorandom string. And what is anything XORed with 0? It's the input. So we can do this and get the transmitter to tell us what its whitening sequence is. So we can implement a receiver, read that out, plug it back in, and then start to solve for the rest. Cool. Next stage is the interleaver. Again, we had that formula from the patent. Surprise, surprise, implemented it. It was no good. So let's figure out how this works. Now, we're going to move very quickly through this because this was the hardest part of all of this. And I'm going to, show you the process without, making you waste all the time of staring at a bunch of graph paper and trying things that kind of went into this. But again, just like with the whitening sequence, we're going to exploit properties of the Hamming effect to reveal patterns in the interleaver. So again, if we look at our Hamming 8.4 code words that we know and love that are very useful, we're going to use this time the code word for 4 ones, or the code word for hex F. And in that case, the state of that code word is 8 ones. So if we construct a bunch of packets where basically we take 8 symbols, or we take 4 bytes, which is 8 symbols in SF8, and we walk the position of those ones through our frame here, we can start to look for patterns. Who sees it? I'll save you the trouble. Who sees it now? Look at the bottom row, second from the right, and you'll see the pattern. Basically, it's a diagonal interleaver, but the first 2, the 2 most significant bits are flipped. So if we take this and then read out, basically we can take this and we can start to map those diagonal positions into positions within a de-interleaved matrix. So if we do that and we walk through all the different states and map those positions out with data that we know, we get this nice table. Now let's put this table next to the data that we're looking for. right? So here we've decomposed the Hamming code words for the data that we passed in, which is, of course, our beloved dead beef. In the middle column on the left, we have the data values, the 4 data bits that we're looking for. And then the right column on the left there are the parity bits that we're looking for. Again, I'm going to make this easy for you. If you stare at this for long enough, you become compelled to reverse the bit order. And then if you continue staring at it, you start to see some patterns. That looks like our data, right? So if we go a step further, we can start to map in some of these Hamming correcting fields into this matrix here. So here we see the 4 data bits are the rightmost bits, and then we can see that parity bits 1 and 2 correlate very nicely. And if we go a step further, we can see that bits 5 and 4 map very closely as well, although they're flipped. You'll see that parity bit 4 is actually more significant than parity bit 3. So we're almost there, right? All that we have left to do is apply our FEC, and we're done. And that's the modulation. That's the whole thing. So again, thank you. So again, let's talk briefly about these red herrings and try to wrap this up. I want to do a demo before our Q&A. So we had these 4 different decoding stages here, right? And we had great documentation for all of them. But empirically, after implementing them, we were able to establish that, well, 3 of the 4 just weren't the case, right? One of them was actually cool, right? One of them was actually what it said it was. So yeah, anyway, how are we able to work through this? I think it's important to reflect and try to get some takeaways from this. Hopefully this is useful as you approach your reverse engineering challenges. Basically, what was essential here was being able to bound the problem and hold certain things constant so that we could solve for unknowns. And if you remember, we kind of did this in 2 stages. We were able to cancel out the interleaving in the forward error correction and hold that static in order to figure out what the whitening sequence and the gray indexing were kind of all in one go. And then when we controlled the gray indexing and the whitening sequence, and we're pretty confident about what the forward error correction was, there was really only one variable that we really had to solve. Really only one thing we actually had to go into the bits and really kind of dig out of this thing, right? So by making these assumptions, using open source information, and really bounding the problem and working through it coherently, we're able to reverse these 4 stages down into really one experimental variable and just solve for it. So that's really the trick here. Okay, I'm going to blow through this next part, talk very briefly about the structure of the LoRa PHY packet. So this is a picture pulled out of one of the data sheets. We already talked about the preamble, those repeated chirps. One thing that's not pictured here is the sync word and the start of frame delimiter, which is right there. And then we have this thing called the header, right? And it says here that the header is only present in explicit mode. So there's this notion of implicit versus explicit header in LoRa. And the explicit header includes a PHY header that has some information such as the length of the payload, the type of FEC scheme in there that's applied to the remainder of the payload, not the header itself, but the rest of it. And then there's also an optional CRC as well that can be included. And implicit assumes that the receiver knows the modulation parameters and skips that bit. So no problem, right? We can use implicit mode, figure out what the whitening sequence is, and then switch back to explicit mode, use the whitening sequence from implicit, and figure out what the header is by just looking to see what the values are as we change the modulation. Yeah, right. None of this is easy, right? Like, they really nothing helps us here. So, as it turns out, implicit and explicit header modes use different whitening sequences. So the PHY header remains obfuscated even if we know what the implicit whitening sequence is, the implicit mode whitening sequence is. So let's see what we know. Again, we've got this header here, and in this picture it tells us that the code rate is always 4.8 for the header. So no matter what the code rate, that is the number of bits in the Hamming forward error correcting codes used is for the rest of the packet, this code rate is always 4.8. Well, what about the spreading factor? As it turns out, the header is always sent at the spreading factor that is 2 less than the rest of your modulation. The code rate is still 4.8, but the spreading factor for the header is spreading factor -2, so 2 fewer bits per symbol, even if the header is implicit. And I have to credit Thomas Telkamp for giving me the tip that actually led to kind of putting this all together. Thanks to him. So again, the first 8 symbols, no matter whether you're in implicit or explicit mode, are always sent at SF-2 and code rate 48. That's always the case. Also, there's this mode called low data rate, where if that's set on, then all of the symbols in the remainder of the PHY packet are also sent at spreading factor SF-2. So it's just an extra, it basically gets you some extra margin in case you're dealing with a noisy channel and need to get data through. That's the PHY. Who wants some tools to go with it? Who's curious about this and wants to start playing with it? Does LoRa seem cool? So with that, that brings us to GR LoRa, which is an out-of-tree GNU radio module that I've been working on for the last couple months. And it's an open source implementation of the PHY that works very nicely with the GNU radio, software-defined radio, digital signal processing toolkit. It's open source software, so it's free software. It's got a great community built up around it. It's really cool. If you're curious about SDR, there are loads of good tutorials. And even if you're a wizard, well, if you're a wizard, you already know what this is. But it's a really, really great piece of software and ecosystem. And why is having an open source version of this interesting? Well, existing interfaces to LoRa are at layer 2 and above, both with the data sheets that we get that go with each of the different LoRa radios and the standards that are available and open. It's all at layer 2 and up. We don't have any insight into what the PHY state machine actually does. And PHY layer security really can't be taken for granted. And to back this up, I'm going to point to some 802.15.4 exploits that kind of reinforce this. From a couple years ago, we have Travis Goodspeed's Packet and Packet that showed that he was able to do a full 7-layer compromise by basically encoding the data that would induce the preamble and sort of frame symbols for 802.15.4 within the payload of another message. He was able to get some really wonky things to happen to radio state machines in doing so. And related to that, we have this wireless intrusion detection system evasion that was done by Travis Goodspeed and some friends of mine from Dartmouth, where they were basically able to fingerprint how different 802.15.4 radio state machines work and construct packets that would be able to be heard by some but not others. So from that, you could basically bend the PHY, generate versions of packets that weren't totally compliant with the standard, but would still be heard by certain receivers and not others. So some really tricky stuff here. PHYs really matter. You can't take them for granted in the picture of security. So my hope with this is by getting this tool out there, we can actually really start to look at this interface and figure out how it works and how it can be made better, and really start to get involved with improving the security of this new protocol. So there's some prior art to cite. Josh Bloom has a module for Pothos, which is a kind of like a competitor to GNU Radio. It's like another framework. It gets the modulation right, but the decoding is basically off of the documentation. So it can talk to itself, but it can't talk to actual hardware because it doesn't implement the real decoding stage that we had to reverse engineer. And also, there's another GR LoRa out there made by this guy RPP0 on GitHub. When I first looked at it, it was like this Python thing that I couldn't quite get to work. I went and looked at it again last night. It actually looks pretty cool. So you might check that out too if you're interested in this. It looks like it's pretty solid. So my GR LoRa implements modulation encoding into separate blocks so that you can be modular and experiment. So if you want to have like a multiple, kind of like a common 2-layer forward error correcting thing, in better resiliency, you can write that in without having to touch the demodulator. It's all decoupled for you. Also, there's a very simple asynchronous PDU interface for passing data between the blocks. And you basically write to it just using WebSockets, which is really easy. I'll demonstrate in a minute. And it's just like IEEE 802.15.4, which is a GR IEEE 802.15.4, which is a really great module made by Bastian, who I think is here. Really cool tool. I use it all the time. So the demodulator and the decoding implements the process that we just reverse engineered using the stacked FFTs and all that. The modulator and the encoder use a more efficient method that does direct synthesis of the chirps. So rather than like basically computing the FFT results and then doing an IFFT of that, we can actually index into a pre-computed chirp to make the generation a lot more computationally efficient. If you want the source, it's right there. Just pushed a giant update to it about 2 hours ago. So if you're interested in playing with it, there it is. Let's run through a quick demo before we're out of time here. So here's a scenario. I've written you guys a poem, or I'm going to play you guys a poem, and I want to be able to sniff it and show you what it is, right? So to transmit, we have our Adafruit. It's an Adafruit radio, like an Arduino, basically, with a LoRa radio on it. And to receive it, we're going to use our USRP right down here. And of course, it's all being received by GR LoRa. So I'm going to jump over to my VM if I can. Let me see if I can get this up on the other screen. Bear with me one moment. There we go. Show you all the entropy of my password. We're going to start our receiver here, and now I'm going to just open a socket here, and I'm going to start my transmitter, and let's see what we have for you. In case you're unsure of what you're looking at. So that's all over LoRa. There are a few to-dos. If you want to contribute, be happy to have you do so. Some additional resources if you want to know more. I've written this up all in detail in Travis Goodspeed's POC or GTFO. The most recent issue has that in there. Also, if you want to learn more about radios and SDR, my colleague Mark and I are giving a talk at ShmooCon and Troopers called So You Want to Hack Radios, which is going to go through how to reverse engineer really basic IoT modulations. It'll spend a lot more time on some of the basics and show you how to actually apply this stuff yourself. To wrap up, LPWANs are exploding. They have tons of momentum and are popping up everywhere. RF stacks are also becoming more diverse. So when you're talking about securing your wireless airspace, you're not just worried about Wi-Fi anymore. If you're a corporate security administrator, you're working corporate IT, you also have to worry about all these other like IoT appliances that are coming into your enterprise and are starting to take root. On a technical note, we've shown how to go from some obscure modulation into bits, and we've also added a new tool to the researcher's arsenal. I want to thank Balin Sieber at Bastille. He's an incredible resource, and this wouldn't have been possible without him. Also, the open source contributors who helped get here, helped us all get here, and finally, the Chaos Computer Club for organizing 33C3 and having me. So thank you very much. Thank you for your attention, and I'd be happy to take your questions.
We are almost out of time. Thank you very much, Matt. We're able to take very few and brief questions. So microphone in the front right, please.
I remember you. We met at a new radio conference. Good to see you.
Yes. Are there ways to quantify the reliability of a dense LoRa network?
Could you repeat that, please?
Are there ways to quantify the reliability of a dense LoRa network?
I'm sure there are. I haven't really looked at all at benchmarking or figuring out what kind of the limits of the PHY are. My interest has really been in getting the decoding and information extraction done. I know that there's a group in San Francisco that's building, they're called Beep Networks. They're building a LoRa product or network of some sort. They've done some benchmarking of how well LoRa works in cities, and they have a blog post that's pretty good. You might check that out.
We have one question from the internet via our Signal Angel.
Our panel on the ISC is asking, how long did it take to figure out all of this?
So, I first saw LoRa in the wild in January and kind of just let the capture sit in my my hard drive for a while. It probably took about 4 or 5 weeks of working on this more or less full time. I had some other things working on too. I'd say probably 4 weeks from when I actually said, all right, let's figure this thing out, to having the initial results.
Another question from the rear right microphone.
So in decoding those two unknown layers, you had your proprietary hardware, and you could send it data, and it won't do the AES and encryption stuff, and it just sends that with its encoding?
That's a great question. I kind of skipped over that. The microchip LoRa radio that I had, this guy right here,
yeah.
I also looked at another one that was a LoRaWAN radio. This is a LoRaWAN radio, but actually exposes an API to pause the max state machine. So you can turn off all of the layer 2 stuff that would add a header and encryption and stuff like that, and send what are close to arbitrary frames. And when I say what are close to arbitrary frames is because you can't turn off the implicit header. So it's always an implicit or sorry, you can't turn off explicit headers. It's always in the explicit header mode. So this more or less exposed raw payload injection.
Okay, thanks.
We're already in overtime. We're taking one last question from our signal angel on IRC, and then we'll have to wrap up.
I'll be happy to hang out and answer questions after the fact, too.
Now, many people are wondering what implications does it have that basically the patent is not used at all? So could you say that this technology is patent-free in a way?
I am not a lawyer, but I have known lawyers, and I know that they're clever enough to not fall for that. So I'm sure that the patent was defined as generally as possible, and again, it describes a modulation similar to LoRa. I'm again not a lawyer, but I'm almost certain that it would be covered. So, but that's a clever thought.
Thank you, Matt Knight. Please give him a warm round of applause.
Thank you again.